Hello, Kim 120. Yes, we are ready for lecture 2 of 3 for chapter 7. So the last lecture really focused on light, electromagnetic radiation, and thinking of it as both a wave and a particle. So the particle of light being a photon, and we talked a lot about the wave-like properties at the beginning of the last lecture, and then graduated into particles. So now we're going to use that same logic and translate it to electrons in an atom, which is very cool. Okay, so this image here is a diffraction pattern. So this is the image that is created when you shine, and this particular image is when you shine a X-rays at a nickel alloy plate. So we know that those X-rays are comprised of photons, which have both particle and wave-like properties. And this diffraction pattern is a really clear indication that these photons are also waves. So these areas of greater intensity would be areas where we have constructive interference with that wave. So this is when you have two waves that are moving kind of like in tandem, and they're going to match each other and amplify that wave. So we get a brighter light, greater intensity. In contrast, we have these areas where there is no light, and that would be areas where you have destructive interference. So this is where the waves are out of phase. So we call this in phase and out of phase. When they're out of phase, they essentially cancel each other out. So you can think about ripples on water and kind of visualize that to help you imagine what this looks like. Okay, so what's really interesting about this is, we had started to develop this understanding of light as a wave and a particle, and it was pretty natural for scientists to then say, okay, well, what about electrons? Up until this point, we're really thinking about electrons as particles, and the question was, do electrons also exhibit this particle-wave duality? So to test this theory, electrons were shot at a nickel alloy screen, and the same pattern arose. So now we have a photon being a particle and a wave, and we have an electron being a particle and a wave. And in fact, this is like a really big concept. All matter exhibits both particulate and wave properties. So the smaller the matter is, like when we're looking at it on the scale of a photon or an electron, we tend to think of that or experience it more on the wave level. But when you have larger pieces of matter, like a human being, we experience that as matter. We actually can't quantify the wavelength that we're giving off. But we are both, which is cool and wild to wrap your head around. Oh, come on. Sorry. Okay, so if we take white light and we shine it through a prism, so this is white light. Remember, white light is like sunlight. It contains all wavelengths of the visual spectrum. So we shine white light through a slit and have that diffracted by a prism. What that's going to do is those different wavelengths of light get separated out by the way that they move through this prism. You probably maybe grew up like I did with one of those prisms hanging in like your kitchen. I don't know why it would have to be your kitchen, but it is. And you get rainbow patterns all over your floor, and you're a kid and you're like, that's awesome magic. Okay, so if it's white light, it gets separated into the colors of the rainbow. So what happens if we're not looking at white light, but instead we're looking at hydrogen gas? So if we do the same process with hydrogen gas, we get these very discrete bands. So what this is called is the hydrogen line spectrum. And it shows us that hydrogen gas is not capable or does not possess all wavelengths of light. Instead, it's these discrete values. So the question, of course, is why does that happen? And our first, I guess the person who kind of put all of these pieces together is Niels Bohr. And so he is a classic physicist, and he was thinking about the electron traveling around the nucleus as a wave and a particle, and was really focused on explaining this, these discrete bands in the hydrogen gas spectrum. And he hypothesized that it was because the electron could only orbit the nucleus in these a certain radius from the nucleus, and that the emission spectrum that we were seeing is those electrons in orbit around the nucleus being excited to a more distant orbit and then relaxing back down or coming back down to their ground state closer to the nucleus. So one big concept here that we should talk about before we go too far is you want to think about, okay, this is our nucleus. If our electron is orbiting close to the nucleus, that negative charge is really attracted to our positively charged nucleus. And so that electron is going to be at a pretty low energy level, right? Again, think of this as like magnets. If, however, our nucleus is here and our electron is much further away, so in this case we'd be thinking about it as a higher energy level orbit, this is going to be a less stable electron. It's going to be easier for that electron to interact with other things in its environment because that pole of the nucleus is felt less. So we would say that this electron is at a higher energy state. It is less stable. Okay, so Bohr developed this equation, which is going to represent all of the energy levels available to the hydrogen electron. So Z here is just our integer. In this class, we're always going to be just looking at hydrogen, so Z will always equal 1. And that's just specific to this equation. It gets much more complicated when you have more electrons, when you have more orbits that you're working with. So we're going to keep it pretty simple and just use this classic equation for hydrogen. Okay, so the wavelength represented here would be our jump from n equals 1, so this is the nucleus, and here we have n equals 1, and if that electron gets excited to the next orbital, it will only stay there for a brief period of time, for as long as it can maintain that higher energy state, and then eventually it will decay, so it'll go from this n equals 2 down to n equals 1. Now, it's losing energy. We know that energy in the universe is conserved, so that energy is expelled as a photon of light at a particular wavelength. In this case, that wavelength would correspond to red on our visual spectrum. This green on the hydrogen line spectrum would be that electron absorbing enough energy to get to n equals 3. Again, it'll only stay there as long as it has that energy source. It's not as stable here, so then it will naturally decay. And when it does, that energy is a photon. That's a photon of light. Okay, same concept here. So because our electrons are are restricted to certain orbits. Let's say orbits of a particular radius. They can only emit photons when they decay back to their ground state of certain wavelengths. This is going to give us our spectrum for our different gases. Okay, so one of the rationales for this particular, these like specific orbits is the concept of a standing wave. So you can, if you're not sure what a standing wave is, I recommend just like going on YouTube. Actually, one of the videos that you've definitely watched talks about standing waves. So the idea here is that this is a standing wave. You have the electron orbiting around the nucleus, and it's really stable, and you have, in this case, 4 half wavelengths. Here, we have the same thing. It's a standing wave. We have 5 half wavelengths. So this would be correlating to n equals 4. Think of that as like the 4th radius out from the nucleus. This would be n equals 5. And here is an example of why these radii are very specific. So notice this is a smaller radius, larger radius. This is intermediate between the two. Now, when it's intermediate between the two and you have this set wavelength, you are going to have a mismatch. And in this case, that electron is no longer stable at that orbit. In fact, it can't exist at this orbit. And because of that, it would actually just decay into the nucleus. So this doesn't happen because we only have those allowed orbits. Why? Because our electron is a wave. Here it's stable. This doesn't happen. Okay. So of course, we're chemists, so we're interested in quantifying all of this information. So we just had an equation that I glossed over because we were going to use it in the slide. Now you know. And this is really the form of that equation that we'll use most often. So again, Z is going to equal 1 in this class always, because we're always looking at the hydrogen atom. And then we have N final minus N initial. So N is going to be our orbit, right? So that's going to be that radius concentric circles going out from the nucleus. So what's awesome about this equation and Bohr's work is that we can now look at, okay, an electron going from one radii to another, and the energy that would be emitted as it decays back towards the nucleus, or the energy required to move that electron from its ground state being the closest to the nucleus, the most stable form that electron can be in, or most stable orbit that electron can be in, out to the next higher orbit. So here we have a question. It's like, what wavelength of light would be emitted if an electron goes from n equals 4 to n equals 3 in the hydrogen atom? Again, always going to be looking at it in the hydrogen atom. Okay, so we have n initial would be 4, n final would be 3. So you want to think about this. All right, here's my nucleus. Let's color that in. We have 1, 2, 3, 4. All right, so it started at 4 and it decayed down to 3. So the question is, we know that that energy is going to go somewhere. It's going to be emitted as a photon. What is the wavelength of that energy, electromagnetic radiation? Okay, so initial 4, final 3. So now we're just going to plug that into our equation. So our delta E is equal, this is the Rydberg constant for the hydrogen. 1 over, so this is our final, 3 squared. So students often forget the squared. Can't do that. 1 over 4 squared. Now, I'm not putting 1 squared because 1 squared is 1, and it's always going to be 1, so something to think about there. Okay, so we can think about this as 9, this would be 16, right? Sometimes you're going to be using whole integer numbers because n can only be a whole unit number, right? We saw that mismatch. You can't have a standing wave. You can't have a stable electron orbiting the nucleus if it is not a whole number. So sometimes I like to just go ahead and immediately change those square values to what the number is squared because it's usually really simple math. Okay, so plug this into your calculator and you get that energy of negative 1.06 times 10 to the negative 19th joules. Okay, so what does this number represent? That number represents the energy that is lost by the electron as it moves from n equals 4 to n equals 3. It becomes more stable. So it's giving off that energy. Moving forward, when we answer the question of what type of electromagnetic radiation is emitted, which really means what wavelength is it, you can't figure out one without the other, we are going to just ignore that negative because the negative's from the perspective of that electron that lost that energy and moving from 4 to 3, becoming closer to the nucleus, becoming more stable, but that energy was transferred to was emitted in the form of electromagnetic radiation, otherwise known as light, otherwise known as a photon, or photons. Okay. So now we want to use our equation that we encountered last lecture of the change in energy being equal to Planck's constant over wavelength. So you can see at the bottom here, I've rearranged that equation so that you have wavelengths being equal to Planck's constant times the speed of light divided by that change in energy. So we're just going to plug that in here. Right, so look at your units. You can see that everything's going to cancel out. We're going to be left with our value in meters, and you should get, and you can actually ignore that negative. I kept it in, so I'll just answer this correctly. So it would be negative 1.06 times, oh, sorry. It would be negative 1.9 times 10 to the negative 6th meters. Okay, obviously you can't have negative meters. This is where, remember, that negative value for energy is in relationship to the electron, which lost energy. Now we're talking about the energy of our photon, so 1.9, or electromagnetic radiation, I shouldn't say photon. So this is our wavelength. Now it asks what type of electromagnetic radiation. You can see it's 10 to the negative 9th, so that would be 1,900 nanometers. So it's outside of the visual spectrum. Looking at our electromagnetic radiation chart, I can see that that would fit in somewhere here. So I would say infrared. Or you could say near infrared, which is abbreviated as NIR. Okay, I would accept infrared. I would accept if you just left it with the value. So it's really cool that we can calculate, that all of this experimentation has happened so that we can calculate the wavelength of the electromagnetic radiation that electrons emit as they decay towards the nucleus. Crazy. So this line spectra phenomenon is not unique to hydrogen. It is true of all gases. So your textbook, I think the first photo or image figure for your for this chapter is actually this image, which I really love. It's a collection of gas spectrums. Very cool. Okay, so now we've made this big leap or transition from talking about a photon as being a wave in a particle to now an electron being a wave in a particle, to understanding that the emission spectrum of an element is limited by that radius of those orbits, and that those orbits are only going to be these discrete values, right? They're not continuous. You can't have like n equals 2.13, right? It wouldn't be a standing wave, it wouldn't be stable. Okay, so now we want to continue developing this idea or these concepts in order to have a model of an atom, a model of electron behavior, because electrons are what are ultimately responsible for bonding and for chemical reactions. So a huge step towards this is Schrodinger's equation, which I forgot to label here. I probably misspelled his name. Shh, it's fine. Let's just make it go away. That's Schrodinger's equation. Okay. So Schrodinger's equation is looking at the probability of a electron's location in orbit around a nucleus. Whew. That deserves a drink of water. Okay. So this is describing, it's the probability of finding an electron. Okay, so moving forward, what we're really going to be talking about is the probability of finding an electron in a certain area in orbit around the nucleus. So one thing to understand is that we've developed these models that really help us predict and understand the behavior of atoms and chemical reactions. And they're sound models, but we are limited by a number of factors. One being like the particle wave duality is just like mind blowing, but also, and part of that particle wave duality is really beautifully summed up in the Heisenberg uncertainty principle. So that's saying that the more we focus on an electron's or any particle, but in this case we're interested in electrons. So the more we focus on an electron's position in space, the less we can accurately know its momentum. So I like to think of that as the more we focus on an electron as a particle orbiting a nucleus, the less we understand its wave-like behavior. So that pattern of movement around the nucleus. Alternatively, if we focus on the wave-like movement, we know less about its individual, about its actual location, which is really cool. So from a combination of Bohr's work, Schrodinger's work, Heisenberg, and countless other people, I'm not a quantum physicist, but so many people, we have a pretty good idea of what electrons' behavior is and what atoms actually look like. So we're going to talk about orbitals a lot moving forward. But this right here is just an example of what we've been able to do using all of these mathematical, chemical, physical principles. So here we have what is called a probability map of an electron in this particular orbit. So in this case, we're looking at the hydrogen electron. So that hydrogen electron is most likely going to be closest to the nucleus. However, it can move further out. And this zone, right, this like colored area is representing the probability of finding the electron there. So the darker it is, the more likely it is, the lighter it is, the less likely. And this accurately, all of that colored zone, the entire gradient of it represents about 90% chance of where that electron is going to be. So we can see that the probability of finding that electron gets higher the closer you are to the nucleus, which makes sense because we talked about how the closer an electron is to the nucleus, the more stable it is. So is a big concept. We don't know the exact position of an electron orbiting the nucleus, only the probability of finding an electron there. Okay, so we're really interested in all of these different locations that an electron can be in. And we've designed a system called quantum numbers. And don't stress about this slide. I'm going to go over each one. But we have these 4 quantum numbers that allow us to really pinpoint an electron. So we're looking at one electron in an orbit around the nucleus of some element, right? So I like to think about the quantum numbers in the context of like going to a concert, which none of us could do because we're in quarantine right now, but I'm sure you've all been to a venue to see music played in the company of others, and one day we will do that again. But I like to think of the quantum numbers as kind of the same thing as having a ticket to that concert. So the last show I went to was, I saw Mark Maron. Yeah, okay, so the last show I went to wasn't actually music. I saw Mark Maron at the State Theater. He was awesome. So I had a ticket to the show. And let's just talk about it in context of exactly what my ticket was. So the principal quantum number would be the same as me saying like, okay, my ticket says that it is at the State Theater, right? It could have been at Space. It could have been at Merritt Auditorium, but no, it was at the Cross Arena, but it was at the State Theater. Yeah. Okay, then L would be like the area of the State Theater that it was in. And I am poor. I'm not poor, but I'm definitely not spending a lot of money for front row tickets. So I was in the balcony, right? State Theater in the balcony. I was in row, it was actually pretty great. I was in row 1 of the balcony. So pretty decent seats. Again, I'm not that poor. And then last, I was in seat 2. Okay, so I was at the show. I saw Mark Maron. Yeah, he's funny. I do not endorse any of his beliefs. Yep. So you have State Theater, balconies, row 1, seat 1. Okay, so this is what my ticket had on it. That's the information. Now, if I got to that seat and someone else was sitting in it, they would be in the wrong seat. No 2 people can occupy the same seat in a theater at the same time. The same is true for an electron orbiting the nucleus. That's where I was going with this. So the quantum numbers really help us narrow down and say, okay, this is where this particular electron is. Again, this is part of a model to help us understand the form of orbits around the nucleus and the possible location, probability of finding an electron. Okay, so the first quantum number is called the principal quantum number. Then we have angular momentum, magnetic number, and then magnetic spin. Okay, so let's work through this. We're going to use this figure of the periodic table. Hopefully you recognize it as that, even without very many elements labeled. So we're going to use this to illustrate all of these quantum numbers. So that's why I just have this in here. Okay, so I'll highlight within this figure and with red boxes to kind of draw your attention to what we're focusing on here. So n is the principal quantum number, and n is going to be equal to the period of the periodic table. And you can think about n also as being like the energy level. So the lowest energy level is going to be n equals 1. And I also like to think of these kind of in the context of Bohr's model, right? So you have the nucleus, you have n equals 1, n equals 2, n equals 3, right? Going out in subsequent circles. Okay, so if you're at n equals 1, that's going to correspond to the elements that are in the first row of the periodic table. N equals 2, second row of the periodic table. N equals 3, third row of the periodic table. So as we go down the rows of the periodic table, our atoms become more complex. As they become more complex, we have more energy shells. And we're going to see that within those shells, you can have a lot of stuff going on. As they become more complex, they're also becoming larger, right? Those outer electrons are at a higher energy level because they're further from the nucleus. So N is the period. Okay, the next value is L, which is called the angular momentum number. We're going to spend quite a bit of time on this one because it has a lot of working parts. But ultimately, what L is looking at the shape of that orbital. So the shapes that we have are S, P, D, F, and G. We totally don't even talk about G. It's extremely unstable, doesn't really get occupied very often. Go for something, just decays. So we will focus on S, P, D, and F, and what we'll see actually by the time we get to chapter 8 is we're really just looking at S, P, and D. Okay, so why? Because those are most of the elements that we work with and that make up biological systems. Okay, so L corresponds to the shape of the orbital, and this is a really big concept. So L can be any range in value of 0 to n minus 1. Okay, so that means that if n equals 0, it means that the shape of our orbital would be an S shape. And L could only equal 0. If n equaled 1, L could equal 0, right? N's never going to equal 0, I'm sorry. So if n equals 1, L would equal 0. If n, that's just not having an atom at all. If n equals 2, then L could equal 0 or 1, right? Can't equal 2 because L is limited to n minus 1. So what this is really saying is that if you have a atom that has 2 shells, so I like to think of N as these shells that contain multiple different kinds of orbitals, as we'll see in a second, then you can either have S-shaped orbitals or P-shaped orbitals. Okay, so let's take a look at what the heck I'm talking about. Okay, so if L equals 0, so going back to what I just said, if L equals 0, that would mean that N equals 1. At least 1, of course. You are going to have an S orbital. So S orbitals are going to be species in group 1A or 2A. Those are going to be the parts of the periodic table that are first filled in that in the kind of building of more and more complex atoms. So S orbitals correspond to this area of the periodic table. We're going to come back to that, so don't stress out about that right now. I'm just trying to orient you as we work through this. So if L equals 0, then we have S orbitals. So an S orbital has a spherical shape. So again, remember, this is the probability. A probability map of our electrons. So if we have 1s would be n equals 1, L equals 0. So if we're talking about 1s, there's only 2 species that could be just 1s as like what's defining them, and that is either going to be hydrogen or helium. Remember, don't forget this part of our S orbitals. Okay, but we're not limited to having s orbitals just in n equals 1, right? So remember, these are our n values, 1 through 7. Each one of those has an s orbital associated with it. So what's interesting is that you have your 1s orbital, your 2s, and then your 3s orbitals, and going on, right? These are just examples. And they're getting consecutively larger, right? So nucleus, nucleus, nucleus. You're getting larger. They have higher energy because they're further away from the nucleus. And between our consecutive s orbitals, we have this area of very low, essentially 0 probability of finding an electron, and those are called nodes. And that's going to correspond to that fact that electrons are orbiting the nucleus as standing waves. As such, they only have like these discrete orbits that they can be in. So here, if we had an n equals 3, we have 3 levels to that s orbital. And we would have 2 nodes. So a node separating n equals 1 and n equals 2 s orbital, and then a node between the second s orbital and the third. Okay, so that's an s orbital. S orbitals are spherical. Then we have p orbitals. Oh, and actually, let me go back here. So s orbitals, they're spherical. They are separated by a node. And another big concept, an s orbital can hold 2 electrons. Okay. Now we're ready for p orbitals. Okay, so our p orbitals are going to be represented with this part of the periodic table. Again, we're going to get to that and exactly what I mean by that when we start looking at electron configuration. So just keep this orientation on the periodic table in your mind as we're moving forward. So p orbitals would have this L equals 1. So in order for L to equal 1, we know that p orbitals only exist at n of greater than or equal to 2, right? Because L is 0 to n minus 1. So in order for L to equal 1 and to have a p orbital, we have to be in row 2 of our periodic table, or higher. Okay, so p orbitals are going to have a different shape than our s orbitals. So p orbitals are like lobes. You can think of them as being like a figure 8. And this point here on our figure 8 is going to be our node. So node, again, is that area where you have a very low probability, almost 0, of finding an electron because there's too much interference, right? So this would be our node here. This is an actual electron probability map using Schrdingers Equation. Very cool. So you can start to see where we get, right? These are all mathematical and physical principles that lead us to these shapes. So a p orbital is actually going to be composed of 3 lobes. So we have those lobes, we define them by their orientation to each other, which would be px, py, and pc. All right, in accordance with the axis that they are on. All right, so that's L equals 1, that's a p orbital, that's what it looks like. If L equals 2, then we are in d orbital territory. So, so remember, s orbitals can occur at any n level, right? N equals 1, you have an s orbital. N equals 2, you have an s orbital, and you also have p orbitals. you can only have a d orbital once you get to an n equals 3. So n has to be greater than or equal to 3 in order to have a d orbital. What that really means is we're talking about elements that are in row 3 or higher of our periodic table. All right, and this is the shape of our lobes for a d orbital. They're more complex. Really interesting. I love these probability maps. And this one looks like a pacifier. I don't know why, but it does. Okay, and the last one that we're going to be looking at is if L equals 3. So remember, L is limited to 0 to n minus 1, so that means that n has to be greater than or equal to 4. So only once we're in this row, terrible arrow, of the periodic table can we be talking about, are we going to start having F orbitals fill? Okay, increasingly complex. So these are the kind of model of what those F orbitals look like. Pretty cool. Okay, so we had N is our row of the periodic table. L is talking about our individual shapes. Now we have ML. So ML is going to be talking about the lobes in relationship to each other. So the range for ML is going to be negative L to L, which is inclusive of 0. As you can see here, what I'm trying to show is that we're really kind of grouping each of the orbitals into these groupings of 2, into these pairs. So remember, this is an S, this is our P, these are our D, and this is our F. And now our M sub L, right, those are all corresponding to our L's. N sub L is where we're saying, okay, this is basically looking at one lobe. S only has one lobe. D, we can divide that section into 5 parts, comprising 2 columns each. That corresponds to all 5 possible lobe or kind of orientations of those electrons. P has 3 possible MLs. Sorry. And F has 1, 2, 3, 4, 5, 6, 7. Okay. So what does that actually mean, right? So if L is 0, we're talking about an s orbital. S orbitals are represented in our column 1 and column 2 of our periodic table. I said when we were talking about s orbitals that they can only hold 2 electrons. So that means is like if n equals 1, then L would equal 0, right? Because L is limited to n minus 1. ML would also equal 0 then, right? However, if n equaled 2, L could have 2 possible values. L could be 1 or it could be 0. So if it was 0, then our ML would be 0. But if L equals 1, ML could be -1, 0, or 1. So you have these 3 possible lobes it could fall into. It follows that you would be talking about a p orbital, right? So if L equals 1, we know that's a p orbital. Our n sub L is -1, 0, and 1. So what we're really identifying there is, like the row at my Mark Maron show, is which one of these lobes are we in? X, Y, and Z. sorry. And then D, we have the same concept, right? So if L is 2, we have a d orbital. Within the d orbitals, you can have the range, remember, negative L to L, inclusive of 0. So these are our possible values for n sub L. That's going to correspond to these 5 different lobes, or like suborbitals, however you want to think of it, in that particular orbit. Okay, the last one is magnetic spin, which is a really kind of cool principle. So when we're looking at, let's just keep it simple with an s orbital, right? So I said s orbitals can house 2 electrons. So that's one orbital, right? You've got your nucleus, and then you have your electrons around it. And I'm saying that it can hold 2 electrons, right? So you might be thinking, well, okay, that's a little weird because electrons are negatively charged particles. Why would they want to be in the same orbit together? Or how could they exist in the same orbit together? And this is defined by the Pauli exclusion principle, which I didn't write here, but that's okay. And basically you want to think about, so electrons they have momentum, they're constantly spinning around the, they're constantly moving around the nucleus, and they're also spinning. And so an object that spins is going to generate what's called a dipole. And so basically you want to think about the electrons. In order to exist in the same orbital and not repel each other, they have to spin in opposite directions. What that's going to do is allow them to have moments where each electron is generating a tiny magnetic field where you have an area of greater positivity and greater negativity. So you're creating a dipole, if you remember that from, I don't know, one of my many conversations about water. So you have these moments of attraction between those 2 electrons, which is stabilizing. And so long as those electrons are traveling or spinning in opposite directions, they're going to be able to travel around the same orbit together. So those directions are either going to be negative 1/2 or positive 1/2. Okay, so this is just getting us down to like seat in a stadium level, right? So as soon as you get down to m sub s, you're just talking about 1 electron that could possibly be occupying that space. Okay, so let's just do like a quick overview here. So if we have our n equals 1, our only option for L is 0, which means that you only have an s orbital. That means that I don't have lobes in relationship to each other, right? So the only possibility I have is a minus 1/2 spin or a plus 1/2 spin. If n equals 2, now we're on the second row of the periodic table, we can have an L that equals 0, which again would be that s orbital, which means that I just have a plus or minus 1/2 ms. But I could also have an L which equals 1, which is a p orbital. So my options for m sub L is negative 1, 0, and 1, corresponding to my px, py, and pz lobes of my p orbital. Now within each one of those px, py, and pz, I can have an m sub s of plus or minus 1/2. So your recitation packet, and very annoyingly OWLS has you do a lot of these, you could have, if I was talking about one particular electron, I could say, okay, n equals 2. My L equals 1. So I'm talking about the p orbital in my n equals 2 shell. My m sub L, let's say, is negative 1. So I would have ms values of either positive 1/2 or negative 1/2. So I'm just going to say positive 1/2. This would be this electron's concert ticket. No other electron can occupy that zone at the same moment in time. There's a lot of practice with this in your recitation packet. I highly recommend that you just work through a few of the problems and get your feet under you. But this whole exercise kind of simplifies to a couple principles that I really like to focus on and are going to be really helpful in the next lecture when we talk about electron configurations. So N is your row of the periodic table. L is your shape. So that's going to be S, P, D, or F orbitals. And we've seen examples of what those look like. M sub L is really what lobe? Right? That question of what lobe or which lobe you're in isn't relevant to S because you only have that one lobe, though it's a sphere. And then M sub S is what direction of spin. That helps me kind of break things down a little bit. Further, let's just look at L, ML, and S. So L is really, is it an S, a P, a D, or an F orbital, right? Corresponding to an L equals, well, 0, 1, 2, and 3. Okay, so an S orbital just has an M sub L of 0, sorry. So that means that there's only one orbit. It can only hold 2 electrons. Our M sub L, right, so this would be 0, so it only holds, oh, shoot. All right, let's start over, just for fun. Damn it. That's my one complaint about this program. Okay. Lovely. Okay, so L corresponds to our shapes. Let's just forget about ML, MS, all of that. Let's just break it down really simply. So we have S, we have P, we have D, we have F orbitals. Number of lobes within that is going to be, there's just one here, there's 3 here, right? So this would be like 3 possibilities, right? This is 5, and this is 7. So then we would have our MS, right, of our plus or minus 1. And that's telling us really how many electrons could possibly be in that entire orbit. So S orbitals only have room for 2 electrons. P orbitals have room for 6 electrons. D orbitals have room for 10 electrons. And F orbitals have room for 14 electrons. Now, this is something that we're going to get to in the next lecture. If you look at your periodic table, we highlighted this region for S, and notice there's 2 columns. We highlighted this region for P, there's 6 columns. This region for D, there's 10 columns, and this region for F is 14. So all of these relationships, which are, I understand, like a little overwhelming at first, are really concisely demonstrated or modeled for us on the periodic table. Okay, so get some practice with those quantum numbers because it's going to help when we transfer to electron configurations. And this is just a electron probability maps, which are really cool.